Mechanics. Problem. Rotating elastic rope. A ball of mass big M is attached to the end of an elastic rope of mass small m, the length of which in the undeformed state is L0. The rope with the ball rotates in a horizontal plane around an axis passing through the other end of the rope. The ball slides on a smooth surface. The rope does not sag. How does the distance of the ball to the axis of rotation L depend on the angular velocity omega? When the rope is stretched, the change in its cross-section S can be neglected. The rope obeys Hooke's law for any deformation. Young's modulus is equal to E. Solution. First condition we can mention very useful, which we can use later. It's tension in the end of the rope. Because this rope is rotating, we can write this equation. Tension in length L equal mass of ball multiplied by distance of this ball from axis of rotation multiplied by omega square. So this is the first one. Next, let's write a Newton equation for small mass dm, which is rotating on some kind of distance x from the axis of rotation. For this mass we have a similar equation, that change of tension equal dm multiplied by x multiplied by omega square. But from other hand we can write what is dm in free state and in stretched state. We have these equations, that dm equal rho x, which is density of this rope in stretched situation, multiplied by cross section S and multiplied by stretched length dx, and that's equal to same mass dm in unstretched position with density rho 0 multiplied by same cross section and multiplied by unstretched length dx0. Now let's write Hooke's law for this part of rope. Hooke's law looks like this. We have tension equal negative cross-section multiplied by Young modulus by dx minus dx0 over dx0, which is relative stretch of this part of rope. Or that's equal to negative se multiplied by dx over dx0 minus 1. But from other hand we can write what is this relation dx over dx0 connected to linear density. Of course it's back proportional to length, which we can take from this equation. So we have dx over dx0 equal rho 0 over rho as a function of x. And now we can use all these expressions to find how is rho depend from x. So for dm we have this expression, and we can put this expression in this equation. And also we have tension, and we can count what is dt when we insert this expression to here. So what do we have? Let's write it down. We have this equation, and we got this rho 0 over rho square from this dt, when we insert this rho 0 over rho, and we got this derivative. So this is our differential equation, which connects our density with the distance x. Or finally we can rewrite it like this. We have to integrate this expression, and in limits from x to L, because in point L we already have this expression, so that will help us to find what are our body conditions. So after integration of this formula from point x to point L, we got this expression. And now let's use this knowledge and use this expression for tension when we put here rho over rho in point L. So now we can write the expression for tension in point L. From one hand it's ml omega square, this one, and using this formula, when we put rho 0 over rho, we will get this expression. And from this formula we immediately can find what is rho in point L and insert it in this formula. We will get exact dependency, how is rho depends from x. So from this expression we can find what is rho in point L. This is this expression, and now we can put this rho here and find what is dependency, how is rho depend from x. From this equation we can find what is rho as a function of x, and we will get this formula where a big and a small are constants, and this constants looks like this one and this one. So we got the main result. Now we can use knowledge that total mass of rope equal m small, but this mass we can find using integral for rho x dx from point 0 to point L. Let's write it. So we have this mass, small mass, equal integral from this s multiplied by rho dx from point 0 to L. That will be this integral, and this integral equal just arc sine L over A. Now we can rewrite this expression in form of sine, like this. And after we put a big and a small, we will get this expression. This formula giving us a dependency of L in from omega in this functional way, and this is the answer.